Welcome! Today, we'll be diving into LeetCode problem number 549, titled Binary Tree Longest Consecutive Sequence 2. This is a fascinating problem that challenges us to think deeply about traversing binary trees and finding optimal solutions. Let's explore the problem, understand the approaches, and break it down step by step. Let's get started. In this problem, we are working with a binary tree where each node contains a unique integer value. The task is to find the longest consecutive sequence path within the tree. A consecutive sequence is defined as a path where the values of adjacent nodes differ by exactly 1. This sequence can either increase, like going from 4 to 5 to 6, or decrease, such as moving from 6 to 5 to 4. The path doesn't need to start at the root or end at a leaf, but it must be a connected path within the tree. The input to the problem is the root of the binary tree, where each node holds an integer value and may have left and right child nodes. The output will be an integer that represents the length of the longest consecutive sequence path in the tree. To better understand the problem, let's look at a few examples. In the first example, the binary tree has the following structure. The root node is 1, which has a right child 3. The node 3 has 2 children, 2 on the left and 4 on the right, and the node 4 has a right child 5. The longest consecutive sequence in this tree is the path 3 to 4 to 5, which gives us a length of 3. While there are other paths, such as 1 to 3 or 3 to 2, these are shorter and don't maximize the sequence length. In the second example, the binary tree has a root node of 2 with a right child 3. The node 3 has a left child 1. In this case, the longest consecutive sequence path is either 2 to 3 or 3 to 1, each with a length of 2. It's important to note that the sequence cannot include non-adjacent nodes or wrap around the tree. In the third example, the tree has a root node of 10, with 5 as its left child and 11 as its right child. The longest consecutive sequence here is from 10 to 11, with a length of 2. The path 10 to 5 does not qualify because the difference between the values is greater than 1. Now, let's consider some edge cases. If the tree contains only a single node, the result is simply 1, as the path length is 1. Similarly, if all nodes in the tree have the same value, no consecutive sequence exists, so the result is also 1. Another important scenario is when the longest path alternates between increasing and decreasing values, such as 4 to 5 to 4 to 3. The solution must handle transitions in both directions. Finally, for large trees with multiple branches, the solution should efficiently compute the result while adhering to the constraints, ensuring it performs well even when the tree has up to 3,000 nodes. When tackling this problem, one straightforward way to approach it is using a brute force method. The intuition behind this approach is to traverse all possible paths within the binary tree and check if each forms a valid consecutive sequence. To implement this, we could use a depth-first search, or DFS, which would allow us to explore every path starting from every node in the tree. A few important things to note here are that a valid consecutive sequence must have absolute differences of exactly 1 between adjacent node values, and we need to handle increasing and decreasing sequences as separate cases. However, this method comes with significant drawbacks. The main issue is the computational cost. It ends up repeatedly solving overlapping subproblems for each node, which leads to inefficiencies. For trees with many nodes or great depth, this approach becomes impractical because its time complexity grows exponentially in the worst case. To address the inefficiencies of the brute force approach, we can use an optimized recursive DFS strategy. The key insight here is that instead of exploring all paths naively, we can compute the longest consecutive sequence by focusing on each subtree independently. For each node, we calculate 2 key values, the longest increasing path and the longest decreasing path that start at that node. By combining these 2 paths, we can determine the longest sequence that passes through the node. This is achieved efficiently through post-order traversal, where we process child nodes before their parent. The process involves defining a helper function, DFS, node, which computes 2 values, inc, the length of the longest increasing path, and dec, the length of the longest decreasing path starting from the node. At each step, we compare the node's value with its children to determine if they extend either path. The global maximum length is then updated by combining these paths, and finally, the inc and dec values are returned to the parent node, allowing the computation to propagate upward. The optimized approach is not only conceptually elegant but also highly efficient. The time complexity is O, n, where n is the number of nodes in the tree, since each node is visited exactly once during the traversal. The space complexity is O, h, where h is the height of the tree, as the recursion stack depth is proportional to the tree height. This makes the approach scalable, even for large trees. After evaluating different methods, the optimized recursive DFS approach stands out as the clear choice because it effectively leverages the structure of the tree. By processing nodes in postorder, it avoids redundant computations and ensures that all results are computed efficiently. In contrast, the brute force method is far less efficient, as it redundantly examines all possible paths without taking advantage of the tree's natural recursive structure. While the optimized method does require careful bookkeeping of the inc and dec values at each node, this added complexity is well worth the significant performance gains it provides. The pivotal realization that makes the optimized approach so powerful is understanding how the longest consecutive sequence at a node can be derived by combining independent increasing and decreasing paths from its children. This insight transforms the problem into a local computation at each node, where the results naturally propagate upward through the tree. By breaking the problem into these smaller, manageable pieces, we achieve both clarity and efficiency. In summary, the optimized recursive DFS approach strikes the right balance between simplicity and performance. It avoids the pitfalls of brute force computation and leverages the recursive nature of the tree structure to solve the problem in an elegant, scalable way. This makes it the ideal solution to the binary tree longest consecutive sequence 2 problem. To solve the problem of finding the longest consecutive sequence path in a binary tree, we first need to break it down into smaller, manageable subproblems. For each node in the tree, we calculate 2 key values, inc_len, which represents the length of the longest increasing sequence starting at the node, and dec_len, which represents the length of the longest decreasing sequence starting at the node. The final result is derived by combining these values for each node. Specifically, we take the sum of inc_len and dec_len and subtract 1 to account for the fact that the node itself is counted in both sequences. To compute these values effectively, we employ a postorder traversal, which ensures that we process a node only after its children have been processed. This traversal order is crucial because the sequence lengths at a node depend on the sequence lengths of its children. Additionally, we'll design a recursive function to calculate these values and use a global variable to keep track of the maximum sequence length as we traverse the tree. The recursive function, DFS, node, is the core of our algorithm. It calculates the inc_len and dec_len for a given node and returns these values. The base case for this function is straightforward: if the node is null, there are no sequences, so we return 0, 0. For the recursive case, we initialize both inc_len and dec_len to 1, since the node itself forms a sequence of length 1. Then, we check the left child. If the left child's value is 1 less than the current node's value, it forms a decreasing sequence, and we update dec_len. Conversely, if the left child's value is 1 greater, it forms an increasing sequence, so we update inc_len. We perform similar checks for the right child. After calculating the sequence lengths for the current node, we update the global maximum using the combined lengths of the increasing and decreasing sequences, subtracting 1 to avoid double counting the node. Finally, the function returns the inc_len and dec_len values for further use by its parent node. The efficiency of this algorithm lies in its time complexity. Since we visit each node exactly once during the postorder traversal, the algorithm runs in O, n, time, where n is the total number of nodes in the tree. At each node, we perform a constant amount of work to calculate the sequence lengths and update the global maximum, making the process highly efficient. Several key insights help us achieve this result. Postorder traversal is ideal because it ensures that we have the necessary information from a node's children before processing the node itself. By dividing the problem into the smaller tasks of calculating inc_len and dec_len for each node, we simplify the overall solution. The use of a global variable to track the maximum sequence length eliminates the need for revisiting nodes, further optimizing the algorithm. Additionally, carefully handling edge cases ensures the algorithm is robust. For instance, in a single node tree, the result is 1, and in trees with no consecutive sequences, each node is treated as its own sequence. The recursive DFS function is supported by a function stack, which is implicitly managed by the system during recursion. Now, let's look at the pseudocode to summarize the algorithm. We begin by initializing a global variable, global_max, to 0. This variable will store the length of the longest consecutive sequence found during the traversal. The DFS function starts with a base case. If the current node is null, it returns 0, 0, since there are no sequences. For non-null nodes, we first perform a post-order traversal by recursively calling DFS on the left and right children. This gives us the sequence lengths for the left and right subtrees, which we use to compute the sequence lengths for the current node. Initially, both inc_len and dec_len are set to 1 to account for the node itself. We then check the left child. If its value is 1 less than the current node's value, it extends a decreasing sequence, and we update dec_len. If its value is 1 greater, it extends an increasing sequence, and we update inc_len. Similar checks are performed for the right child. For the right child, if its value is 1 less than the current node's value, it contributes to the decreasing sequence, so we update dec_len. If its value is 1 greater, it contributes to the increasing sequence, and we update inc_len. Once these checks are complete, we update the global maximum sequence length by taking the maximum of its current value and the sum of inc_len and dec_len, subtracting 1 to ensure the node isn't double counted. Finally, the DFS function returns the updated inc_len and dec_len values for the current node. The main function, longest consecutive path, calls DFS on the root node to initiate the traversal and returns the value of global_max as the result. This approach ensures that we efficiently compute the longest consecutive sequence in the binary tree while handling all edge cases, such as single-node trees or trees without any consecutive sequences. Here, we start by defining the structure of a binary tree node with the treenode class, which includes a value, a left child, and a right child. Then, in the solution class, we define the function longest consecutive that will find the length of the longest consecutive sequence in the binary tree. We initialize a variable self.max_length to keep track of the maximum sequence length found during our traversal. Next, we define a helper function, DFS, to perform a depth-first search on the tree. The DFS function will return two values, the length of the longest increasing sequence and the length of the longest decreasing sequence for a given node. If a node is null, we return a base case of 0, 0, as there are no sequences to consider. Moving forward, we initialize the increasing and decreasing sequence lengths, inc and dec, to 1 for the current node. Then, we check if the current node has a left child. If it does, we recursively call DFS on the left child to get its increasing and decreasing sequence lengths. Based on the relationship between the current node's value and its left child's value, we update the inc or dec variables accordingly. For example, if the current node's value is 1 greater than the left child's value, we extend the decreasing sequence. If it's 1 less, we extend the increasing sequence. Next, we handle the right child in a similar manner. If the current node has a right child, we recursively call DFS on the right child to retrieve its increasing and decreasing sequence lengths. We then compare the current node's value to the right child's value. If the current node's value is 1 greater than the right child's value, we update the decreasing sequence length, choosing the maximum between the current dec value and the right child's decreasing sequence plus 1. Similarly, if the current node's value is 1 less than the right child's value, we update the increasing sequence length. After processing both children, we update self.max_length to ensure it captures the longest sequence we've seen so far, considering both increasing and decreasing paths that pass through the current node. The formula we use, inc plus dec1, accounts for the overlap at the current node. Finally, we return the updated inc and dec values for the current node to propagate this information back up the recursion. At the end, we initiate the DFS traversal from the root node and return the value of self.max_length, which now holds the length of the longest consecutive sequence in the binary tree. Here we start by defining the structure of a binary tree node using a class named treenode. This class includes 3 properties, an integer value called val, and 2 pointers to its left and right child nodes. We provide 3 constructors to handle different initialization scenarios, including a default constructor, one that initializes the node's value, and another that sets both the value and its child nodes. Next, we define the solution class, which will contain the main logic for solving the problem. Inside the solution class, we declare a private integer variable maxLength to keep track of the maximum length of the longest consecutive sequence. Then we define the method longest consecutive, which takes the root of the binary tree as input. In this method, we initialize maxLength to 0 and call a helper method named DFS to traverse the tree and compute the result. The longest consecutive method concludes by returning the maxLength variable, which contains the final result. Now, let's look at the DFS method, which performs a depth-first search on the binary tree. The method takes a tree node as input and returns an array of two integers representing the lengths of the longest increasing and decreasing sequences at the current node. If the input node is null, we return an array with both values set to 0, as there cannot be any sequences. We then initialize two variables, inc and dec, to 1. These will track the maximum lengths of the increasing and decreasing sequences starting at the current node. To explore the left child, we check if it exists. If it does, we recursively call DFS on the left child and analyze its value relative to the current node. If the left child's value is 1 less than the current node's value, it forms a decreasing sequence, and we update dec accordingly. On the other hand, if the left child's value is 1 more, it forms an increasing sequence, and we update inc. We then perform a similar check for the right child. If the right child exists, we call DFS on it and compare its value with the current node's value. If the right child's value is 1 less, we update the dec variable to reflect the longer decreasing sequence. If the right child's value is 1 more, we update the inc variable to account for the longer increasing sequence. After processing both children, we calculate the length of the longest sequence that passes through this node by adding inc and dec and subtracting 1 to avoid double counting the current node. We then update the global maxLength variable if this sequence length is greater than the current maximum. Finally, we return an array containing the inc and dec values, which represent the longest sequences starting at this node in both directions. Here, we start with a simple binary tree consisting of the root node 1 and its two children, 2 and 3. The goal is to find the longest consecutive sequence in the tree. We initialize self.max_length to 0 and begin our depth-first search from the root node, which is 1. When we traverse the left child, node 2, we call DFS 2. Since node 2 has no children, it returns 1, 1, indicating sequences of length 1 for both increasing and decreasing paths. Back at node 1, we observe that 2 = 1 plus 1, which means there's an increasing sequence, so we update inc to 2. Similarly, we traverse the right child, node 3, and call DFS 3. Like node 2, it also has no children and returns 1, 1. Again, we find that 3 = 1 plus 1, so inc remains 2. Finally, we calculate self.max_length as the maximum of its current value and the sum of inc and dec minus 1, resulting in a value of 2. The function returns 2, 1 for the root, and the final output is 2, representing the longest consecutive sequence in this tree. Now, we examine a more complex binary tree where the sequences can both increase and decrease. The root node is 2, with 1 and 3 as its children, and further descendants 0 and 4. Starting with self.max_length at 0, we call DFS 2, and first traverse the left child, node 1. From there, we move to node 1's left child, node 0. Since node 0 has no children, it returns 1, 1. Back at node 1, we check if 0 = 1, 1, which is true, indicating a decreasing sequence. We update dec for node 1 to 2. At this point, self.max_length becomes 2 since it is the maximum of its current value and the sum of inc and dec minus 1. Node 1 then returns 1, 2, reflecting the lengths of its increasing and decreasing sequences. At node 2, we verify if 1 = 2, 1, which is true, so dec is updated to 3. Next, we traverse the right child, node 3, and proceed to its right child, node 4. At node 4, since it has no children, it returns 1, 1. Back at node 3, we find that 4 = 3 plus 1, indicating an increasing sequence, so inc is updated to 2. The self.max_length remains 2 as the maximum of its current value and the sum of inc and dec minus 1. Node 3 then returns 2, 1. Returning to node 2, we observe that 3 = 2 plus 1, so inc becomes 3. We calculate self.max_length as the maximum of its current value and the sum of inc and dec minus 1, which updates it to 5. Node 2 finally returns 3, 3, and the longest consecutive sequence for this tree is 5. Lastly, we consider a binary tree with no consecutive sequences. The root node is 10, with 5 and 15 as its children. Starting with self.max_length at 0, we call DFS 10, and first traverse the left child, node 5. Since node 5 has no children, it returns 1, 1. Back at node 10, neither 5 = 10, 1 nor 5 = 10 plus 1, so there is no update to inc or dec. We then traverse the right child, node 15, which also has no children and returns 1, 1. Again, back at node 10, neither 15 = 10, 1 nor 15 = 10 plus 1, so inc and dec remain unchanged. Finally, we calculate self.max_length as the maximum of its current value and the sum of inc and dec minus 1, resulting in a value of 1. The function returns 1, 1 for the root, and the final output is 1, indicating that no consecutive sequences exist in this tree. The time complexity of this solution is O(n), where n represents the number of nodes in the binary tree. To break it down, the algorithm uses a depth-first search, or DFS, which visits each node exactly once. For each node, the operations include comparing the current node's value with its child nodes to check for increasing or decreasing sequences, updating the lengths of these sequences, and maintaining the maximum length found so far. All of these are constant time operations, which means the total time spent is proportional to the number of nodes in the tree. Therefore, the overall time complexity is O(n). The time complexity remains O(n) across all cases: best, average, and worst. This is because the algorithm processes every node in the tree exactly once, regardless of the structure of the tree. For example, in the best case, a tree with only one node will involve a single constant time operation. In the worst case, such as a highly unbalanced tree or one where all nodes participate in consecutive sequences, the traversal still visits each node only once. Thus, whether the tree is balanced or skewed, the time complexity does not change and stays firmly at O(n). In terms of space complexity, the primary factor is the recursive call stack, which depends on the height of the binary tree, denoted as h. At most, the depth of recursion will match the tree height. For a balanced binary tree, the height is approximately log n, so the space complexity in this case is O log n. However, for a skew tree where all nodes are either left or right children, h equals n, leading to a worst-case space complexity of O(n). Importantly, the algorithm does not use any additional data structures, and all variables used within each recursive call, such as inc, dec, and comparisons, take up constant space. Hence, the auxiliary space usage is O(1). When comparing this optimized approach to a naive solution, the differences are clear. A brute force method might involve evaluating every possible path in the binary tree to determine the longest consecutive sequence. This would require multiple traversals of the tree, leading to a time complexity of O(n²) in the worst case. Additionally, the space complexity would increase as intermediate results for each path would need to be stored. In contrast, the optimized approach relies on a single DFS traversal, reducing the time complexity to O(n). Furthermore, the space complexity is limited to the recursion stack, scaling only with the tree's height, making it O(h). The mathematical justification for the big O complexity lies in the nature of the DFS traversal. Each node in the binary tree is visited exactly once, and the operations performed during each visit are constant time, leading to an overall time complexity of O(n). The space complexity is determined by the recursion stack depth, which corresponds to the tree height, h. For a balanced tree, h is approximately log n, resulting in O log n space complexity. For a skewed tree, h is equal to n, leading to O(n) space complexity. This optimized solution is both time-efficient and space-efficient, leveraging the properties of DFS to handle even large trees effectively while maintaining linear time and minimal additional space requirements. When solving this problem, there are a few common mistakes to watch out for. First, many solutions overlook the fact that valid paths can be both increasing and decreasing. Focusing only on increasing sequences results in incomplete answers, as you miss out on paths with decreasing order. Another frequent issue is ignoring edge cases involving single-node paths. Remember, a single node by itself is a valid consecutive sequence, and failing to account for this can lead to incorrect results in smaller trees. Additionally, it's important to reset the sequence length correctly when traversing the tree. If a node breaks the consecutive pattern, the sequence must reset, otherwise, you risk inflating the sequence length incorrectly. Finally, ensure your traversal is efficient. Without techniques like memoization or pruning, your algorithm might repeatedly analyze the same subtrees, which can severely impact performance, especially for larger trees. Another common pitfall involves confusion about the directionality between parent and child nodes. In binary trees, the parent-child relationship is key. Treating child to parent as valid when only parent to child should be allowed can lead to incorrect results. Now, in terms of interview strategies, this problem is a great opportunity to showcase your pattern recognition skills. Many tree problems require tracking specific properties, like consecutive sequences, and being able to clearly explain how you validate and maintain these properties is important. Recursive strategies are another focus. Interviewers often look for candidates who can effectively pass and merge information during recursive calls, such as sequence lengths. Be prepared to discuss edge cases too, such as empty trees, single-node trees, or cases where no valid sequences exist. Lastly, optimization is crucial. Start with a brute force approach to demonstrate your thought process, but then explain how you would refine it. Discuss trade-offs, like time complexity versus memory usage, to show a deeper understanding of the problem. To broaden your understanding, it's helpful to explore related problems. For example, the binary tree paths problem on LeetCode focuses on identifying all root-to-leaf paths within a binary tree, which shares some conceptual overlap. Another related problem is longest consecutive sequence, but instead of binary trees, it deals with arrays, applying similar principles to a different data structure. You might also look into longest uni-value path, which involves finding the longest path in a tree where all nodes have the same value. Lastly, pathsum 3 is a great problem to study. It emphasizes finding paths with specific target sums, which, like this problem, requires careful traversal and condition tracking. Exploring these problems can help reinforce the techniques and concepts needed to tackle tree-based challenges effectively. Now let's discuss some alternative approaches to solving this problem. Recursive depth-first search, or DFS, is a straightforward choice. It's simple to implement, but it can be memory-intensive if the tree is very deep because of the recursive call stack. Its time complexity is O, n, and the space complexity depends on the height of the tree, O, h. Another option is breadth-first search, or BFS, which is an iterative approach. It avoids recursion but may require additional bookkeeping to track sequence lengths. Its time complexity is also O, n, and its space complexity depends on the tree's maximum width, O, w. Dynamic programming on trees is another powerful method. It avoids redundant computations by storing intermediate results, but it can be more complex to implement and debug. Lastly, there's the divide and conquer approach, which works well by combining results from the left and right subtrees. This is particularly efficient for balanced trees, with a time complexity of O, n, and a space complexity of O, h. Each approach has its trade-offs, so choose the one that best aligns with the problem constraints and your implementation preferences. Great job! We've explored problem number 549 and unraveled its solution step by step. Remember, binary tree problems often rely on solid recursion skills and an understanding of properties like parent-child relationships. Keep practicing these to sharpen your problem-solving abilities. Thank you for watching, and don't forget to subscribe for more content like this. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!